My name is Alexandra Widelund, and I work at Climeon. And Climeon is in the Czech project responsible for providing energy savings using waste heat recovery. And Climeon, we are our business is to develop products converting low temperature waste heat into clean electricity and using ORC technology. And Climeon is a Swedish company founded in 2011. We have today 40 plus products installed and in operation globally, both on land and on maritime installations. We have a product portfolio today that comprises two different products, the HP 150 or Heat Power 150 and the Heat Power 300 Marine. We also have Climeon Live, which is a software for remote monitoring and support of our products. The HP 150 is our proven technology, which already is installed and in operation. One unit delivers up to 150 kilowatt of energy at ideal operating conditions. The product is optimized for smaller vessels or vessels having a limited amount of waste heat available. And with limited amount of waste heat, we here mean thermal energy up to 1.5 megawatt. And the Heat Power 300 Marine is our focus product today. It's capable of delivering up to 355 kilowatt of energy, and it's optimized for larger vessels or vessels with a higher amount of available waste heat. And that is waste heat up to 4 megawatt. And in the Czech project, both of these products are included, and I will show you why later. These are some of our maritime references, which mirror the type of ship that is suitable for our products, and also to where in the world we have delivered today. But what is then waste heat and the Climeon technology? I will now give you a short recap on that, and it might be a repetition to some of you who have seen me talk before. So, on a ship propelled and operated by fuel, less than 50% of the fuel energy is converted to mechanical energy and used for propulsion and to provide electricity to the ship. That means that over 50% of the fuel energy is lost as waste heat in the engine's exhaust gases or in its different cooling circuits. And approximately half of that heat is low temperature waste heat, having a temperature below 100 degrees. And at Climeon, we have a technology that converts this low temperature waste heat into electricity delivered to the vessel grid.
Climeon's technology uses an organic Rankine cycle, a closed thermodynamic cycle used to produce power from low-temperature heat sources. The system operates on a hot water flow containing waste heat and a cold water flow, while utilizing the properties of an organic working media circulating in the system to produce electricity. The organic working media boils at a temperature lower than water, which allows the machine to be productive with low-temperature heat sources. Fed into the evaporator, the cold liquid working media is heated by the waste heat, boils, and becomes a gas. It expands and creates a high-pressure flow. This flow of gas is then condensed by the cold water, creating a low-pressure flow. The pressure difference propels the turbine that drives the generator to produce electrical power. Once the working media has passed through the condenser, the cycle is repeated, ensuring Heat Power 300 can continuously generate electricity, provided both hot and cold water sources remain available.
Yes, so that was the technology. But what actually influenced the actual power output from an ORC? Well, because the power output from an ORC installed on a ship will vary. It will not be constant. So at the large temperature difference between the hot water and the cold water, the ORC has the potential to swallow the most heat and to generate the most electricity. The Heat Power 300 is designed for these temperatures. That is hot water temperatures of between 80 to 100 degrees, Thus, it's ideal for engine jacket cooling water or HT cooling water circuits. And it's also designed for normal seawater temperatures of 0 to 35 degrees Celsius. And with that, it has an ability to produce up to 355 kilowatt of electricity. But the actual input temperatures to the ORC depend on power plant design as well as on the ship operational profile, especially on engine load and on seawater temperatures. However, the power production is also limited by the amount of waste heat that is available for the ORC to use. That is how many degrees that the unit can lower the temperature on the hot water without cooling down the engines too much or using too much energy so that the other waste heat consumers cannot work as planned. And this is an example on how much the seawater temperature actually influenced the power output from, in this case, the HP 300. And this graph shows possible power output at different amounts of absorbed thermal power. So when we have a certain hot water temperature and the seawater temperature of 30 degrees, the net power output is approximately 200 kilowatt. But at the same hot water temperature, but at the 20 degrees colder seawater, the power output increases to around 300 kilowatt. But this is a momentary power output. And because of the many parameters that influence the power output, thorough calculations need to be done for each case to determine the actual energy savings from the heat power units. And these need to be done based upon the actual operational conditions of each ship. And this is one of the things that we have done in the Czech project together with Delta Marine. So what was the Climeon Czech mission and what have we accomplished during this project? Our main task in Czech was to develop and test a future-proof waste heat recovery system based on our existing ORC technology. That was initially further developments of our first product, the HP 150. But when we received data from the Czech project on how much available waste heat there was in the cruise ship, we also included the HP 300 in the project. We also developed a digital model of our ORCs to be included in the digital models of the Czech vessels. We also tested our products in the lab based upon real-life engine data and operational parameters, which we received from the other partners. The ORC prototypes were during these tests confirmed to operate as expected for the simulated and measured real-life conditions of the Czech vessels. Also, the digital models were validated and they were confirmed to provide the right results in the digital master simulations. So our main goal was to show that ORC waste heat recovery is feasible for the Czech vessel. But to achieve that goal and show how the actual energy saving, how much energy actually was saved, we needed Delta Marine simulations for each ship and each ship set. And the results I'm going to show you now are based upon Delta Marine simulations. But first, I will give you a short recap on the Czech vessels, their design and their selected operational profile. And some of this has already been presented by Bia, but I think it's good to show it again. The future cruise ship is based upon data from the Maria Viglia class ship MSC Grandiosa. And Grandiosa has 4 four-stroke main engines installed with a total power of 67 megawatt. And she's originally running on HFO. The main difference from an ORC perspective between the baseline vessel and the Czech vessel is the introduction of the Wärtsilä hydrogen engines, which you just heard Kenneth talk about. Because the hydrogen engines have a slightly higher engine power and are designed for a higher HT cooling water temperature. And that is positive for waste heat recovery. The selected simulated voyage for the cruiser was the 7-day cruise between the 6 Italian ports, as Mia already talked about. And this operational profile lead to quite short legs and quite low speed. This leads to the power demand peaking on slightly above 25 megawatt. Thus, during this voyage, only 2 out of the 4 engines that was installed on the Meraviglia actually was in operation. So this result also in less waste heat for us than can be expected when you just look at the total engine capacity of the ship. And for these simulations, as Mia already told also, this 7 days journey was repeated 4 times with 12 different profile with different weather. And this result in different engine loads, different heat demand from the other heat consumers, as well as different seawater temperatures. Thus, different conditions for the ORC to produce power. And the Czech bulker is based upon the Kamsar Max class ship, and operational data is collected from the 9 simulated long-distance routes worldwide. The different routes have different seawater temperatures, different speed, and different weather. Therefore, we also hear the amount of available waste heat for the ORC will vary. But these different routes that were simulated also makes it possible for us to analyze the operational profile actual influence on ORC power output. The Czech bulker is simulated with the vertically scalable power plant model of the 4-stroke engine. And one model has 6 cylinders with a total power 7.2 megawatt, and one has 8 cylinders with a total power of 9.6 megawatt. Thus noted here is that the bulker engine power is approximately 10 to 15% of the cruiser. The Czech bulker also included other energy savings equipment, such as the sails, the air lubrication system, anti-fouling and gate rudder. And these energy-saving technologies reduce the need for propulsion power, and therefore the 6-cylinder engine was possible to use on the bulker. And that's very good for the environment, and very good for the fuel consumption too, but less good for ORC power production. So when we analyzed the contribution of the ORC, we used the larger 8-cylinder engine. So if we now gather all the ORC-related data for each Czech vessel together, we get this table. And here you see the data either with ORC as a single energy-saving technology or together with other saving technologies as the Czech combo. During their simulated voyage, both the bulker and the cruise ship spends approximately 70% of the year or 6,000 hours at sea, and the rest is in port or maneuvering. And as the bulker operates worldwide, the seawater temperature varies as much as between 7 and 32 degrees Celsius. The water temperature in the Mediterranean, where the cruise ship operates, does not vary that much. And during the year, almost all of the engine capacity on bulker is used, but only 65% of the around 70 megawatt installed on the cruiser. But still in total, there's more engine power used on the cruiser than on the bulker. However, the cruiser also have more heat consumers, which need heat to function. Those are, for example, the HVAC, the galley, and the laundry. And also the HFO version also need additional heat for tank heating and for separators. And further, the thermal energy demand for the other heat consumers varies between winter and summer quite a lot, almost 40%. And to avoid using boilers, the heat to the heat consumers is first supplied from the waste heat streams. This means that the heat for the ORC is reduced. And from these simulations, we also receive the remaining available heat for the ORC. And in the bulker, it peaks at 3.2 megawatts, but averaging on just 1.7 megawatt. And for the cruiser running on the HFO, we have approximately 5 megawatt available, averaging on 2 megawatt. And for the cruiser running on hydrogen, we can actually reach up to 11 megawatt of heat, but averaging on 4 megawatt. So also, if we have another routes with higher speeds selected for the cruiser, the available heat for the ORC can be even higher. And interesting to note here is that even though the Bulker has a much smaller engine, the amount of available waste heat is approximately the same as for the cruise ship running on HFO. And this thermal heat is used to increase the temperature of the hot water in the waste heat recovery circuit serving as input to the ORC. And how much the temperature actually is increased depends on how much heat that is of the higher temperature, that is how much heat that is steam. And based upon what I told you earlier about the Climeon ORC products and their different thermal swallowing capacity, we now see that for the Bulker, the HP 150 is a better match. And with a larger engine and no other energy-saving technology, there is enough heat for 2 HP 150. But for the cruise ship and its available heat, the HP 300 is the better match. And one HP 300 unit is in operation 65% of the time when running on HFO. And when running on hydrogen, 2 units are in operation. The first ORC generate electricity 80% of the time, and ORC number 2 generate energy about 25% of the time. And in theory, it's actually available heat for an additional HP 300, but that would be in operation only for a few percent of the time, so we did not include that in the calculations. And now that we have the different ORC waste heat recovery products installed on the Czech vessels, what are the actual savings? Well, for the Bulker, the ORC units can produce 0.4 to 0.8 gigawatt hour per year during the approximate 6,000 hours that the engines are running at sea. And this leads to fuel energy savings between 1.2 and 2.3%. The higher number when ORC is the only energy-saving technology. And on the cruise ship, with simulations made both for the HFO engine and the Czech hydrogen engine, the HP 300 can produce up to 2 gigawatt hours per year. Thus, fuel energy savings of up to 1.6%. However, as I just said, if the cruise ship has been on another voyage, different routes, these numbers could be different. So for the final findings and conclusions of the Czech project from an ORC perspective, the Czech project confirmed that it's not only engine size, but also other heat consumers and vessel routes that have a great influence on the ORC power output. And also for the Bulker, we can see that depending on operational route, the energy production actually varies as much as 30%. And it might be even more on the cruise ship, which uses the HP 300. The amount of energy produced on the Bulker also reduced the shaft power generation by about 40%. So that actually means that the ORC covers approximately 40% of the Bulker hotel loads. And also, using other energy-saving technologies can unfortunately reduce the heat for the ORC waste heat recovery. But on the other hand, using fuels that require less heat to ensure the right viscosity, such as, for example, hydrogen, can enable more heat for the ORC waste heat recovery. So, implementing ORC waste heat recovery on the Czech vessels can generate fuel energy savings on up to 4.7 gigawatt hour per year and save up to 2.3% of fuel energy consumption. Thus, I can now with confidence say that the Climeon goal with the Czech project to show that ORC waste heat recovery system is feasible for and provide energy savings both on present and future ships is accomplished. So that was all for me, and I want to thank everybody in the Czech project. It's been both a pressure and a pleasure to work with you. And thank you all.